Myself, Abelsi Dixon. I am currently in my second year and pursuing BTech in Engineering Physics. I mainly worked on laser sensor integration, developing proportional derivative controller based on lane curvature, object localization based on LIDAR and image, pedestrian tracking, and reverse mode.
Hi, myself Sharad. I'm a second year engineering student pursuing my BTech in biotechnology. I mainly worked on lane detection, track segmentation, and also in path planning with obstacle avoidance using OpenCV.
I'm Ajinjay, BTech Chemical Engineering student at National Institute of Technology, Calicut. My contributions are in the area of object detection, data annotation, path planning, speed control, and traffic sign control.
And finally, myself Anurup. I'm a BTech Engineering Physics student at National Institute of Technology, Calicut. My major role was in the car designing and creating test models along with data annotation. Now, as we move on to the designing section, the car is designed with two extreme colors of the color spectrum, blue and red. Combining those colors give us an exceptional vibrance to the car model, making it appealing to the viewer's eyes. We have also added the logo specified by NXP along with revealing the tire meshes given by them. I would also like to mention that we have added a mesh for the LIDAR sensor at the rear end of the car.
We have used a HOQ laser distance sensor to detect the presence of any obstacle ahead of the car. This laser can read up to a minimum range of 0.1 meter and a maximum range of 1 meter. It has a field of view of 240 degrees and it takes a total of 720 samples at 30 iterations per second. This sensor measures distance based on the difference between the wavelength when the laser source is reflected by the object. Let us analyze the software architecture of TESSERACT. We have the input as camera feed, laser scan and odometry. We then plan trajectory by passing the camera image to our YOLO object detection model and detect all objects within that frame. Corresponding action is taken based on the traffic objects and obstacles are masked in the image frame and passed to getLane curvature function. This function helps the car to navigate to the center of the visible track of the region considering the obstacles. The error between car's position and base point of the available track is then passed to the proportional derivative controller and corresponding steer value is taken. At the same time, laser scans for 8 region for the presence of obstacles and decide the corresponding steer value. The algorithm also tracks the pedestrian motion based on the synchronized information of the LiDAR and image within object LiDAR localizer function and then takes the corresponding action. The car also keeps tracks of the reverse mode state in case there is a possibility of collision or moving out of the track.
We used YOLO V4 Tiny for our real-time object detection. As YOLO V4 Tiny is the lightest version of YOLO V4, it is promised to have a pretty decent accuracy with highest speed in processing image frames. We trained our model with 21 different object classes. What the algorithm does is that it will try to find all the objects in the image and classify as well as provide the coordinates for the bounding box. And we use OpenCV to draw the rectangle box around each object that it identified. In our dataset, we have objects like turn right as well as turn left traffic sign. In order to classify these objects, we have included a parameter flip is equal to 0 in the configuration file of YOLO V4 Tiny. What it does is that it will prevent the vertical as well as the horizontal flip during the training time.
We have used OpenCV for developing a trajectory planning system with an efficient obstacle avoidance strategy. And this can be explained in 3 steps. Step 1, segmenting the track into binary classes or into track and non-track region. In step 2, we are finding a distance plot between each track point and the nearest obstacle point. In step 3, we are finding out the best trajectory with obstacle avoidance using these plot values. We are also using these path coordinates to find out the track curve direction and center offset value, which gives the relative position of car on the track for the smooth navigation of car. Other than the AIML implementation, we also used Python with OpenCV and NumPy for implementing other algorithms like road curvature, detection of left and right track lane, path planning, center offset, etc.
In order to attain self-driving capabilities, we have added pedestrian tracking based on laser object localization, which enables the person to cross the road based on the direction of motion. We have also added collision avoidance based on information from the laser sensor and track information. The car also switches to reverse mode when blocked by any obstacle based on odometry and reattempt to navigate.